Previously, we learned the concept of independent experiments. In this exercise, we'll see how the seemingly simple idea of independence can help us understand the behavior of quite complex systems. In particular, we'll combine the concept of independence with the idea of divide and conquer, where we break a larger system into smaller components and then use independent properties to glue them back together. Now let's take a look at the problem. We're given a network of connected components, and each component can be good with probability p or bad otherwise. All components are independent from each other. We say that the system is operational if there exists a path connecting point A here to point B that goes through only the good components. And we'd like to understand what is the probability that system is operational, which we'll denote by P of A to B. Although the problem might seem a little complicated at the beginning, it turns out only two structures really matter. So let's look at each of them. In the first structure, which we call the serial structure, we have a collection of k components, each one having probability p of being good, connected one next to each other in a serial line. Now in this structure, in order for there to be a good path from A to B, every single one of the components must be working. So the probability of having a good path from A to B is simply P times P, so on so, repeated K times, which is P raised to the kth power. Note that the reason we can write the probability this way in terms of this product is because of the independence property. Now the second useful structure is parallel structure. Here again we have k components 1, 2 through k, but this time they're connected in parallel to each other. Namely, they start from one point here and ends another point here, and this holds for every single component. Now for the parallel structure to work, namely for there to exist a good path from A to B, it's easy to see that as long as one of these components works, the whole thing will work. So the probability of A to B is the probability that at least one of these components works, or in the other word, the probability of the complement of the event where all components fail. Now if each component has probability P to be good, then the probability that all k components fail is 1 minus p raised to the kth power. Again, having this expression means that we have used the property of independence, and that is the probability of having a good parallel structure. Now there's one more observation that will be useful for us. Just like how we define two components to be independent, we can also define two collections of components to be independent from each other. For example, in this diagram, if we call the components between point C and E as collection 2 and the components between E and B as collection 3. Now if we assume that each component in both collections, they're completely independent from each other, then it's not hard to see that collection 2 and 3 behave independently. And this will be very helpful in getting us the breakdown from complex networks to simpler elements. Now let's go back to the original problem of calculating the probability of having a good path from point big A to point big B in this diagram. Based on that argument of independent collections, we can first divide the whole network into three collections, as you see here, from A to C, C to E, and E to B. Now, because they're independent and in a serial structure, as seen by the definition of a serial structure here, we see that the probability of A to B can be written as the probability of A to C multiplied by C to E, finally E to B. Now, the probability of A to C is simply P because the collection contains only one element. And similarly, the probability of E to B is not that hard knowing the parallel structure here. We see that collection 3 has two components in parallel, so this probability will be given by 1 minus p squared. And it remains to calculate just the probability of having a good path from point C to point E. To get a value for P, C to E, we notice again that this area can be treated as two components, C1 to E and C2 to E connected in parallel. And using the parallel law, we get this probability is 1 minus P C1 to E multiplied by the 1 minus P C2 to E. Note that I'm using two different characters, C1 and C2, to denote the same node, which is C. This is simply for making it easier to analyze two branches where they actually denote the same node. Now, P, C1 to E is another serial connection of these three elements here with another component. So the first three elements are connected in parallel, and we know the probability of that being successful is 1 minus P, 3, and the last one is P. And finally, P C2 to E is just a single element component with the probability of successful being P. At this point, there is no longer any unknown variables, and we have indeed obtained exact values for all the quantities that we're interested in. So starting from this equation, we can plug in the values for PC2 to E, PC1 to E back here, and then further plug in PC to E back here. That will give us the final solution, which is given by the following somewhat complicated formula. Now, in summary, in this problem, we learned how to use the independence property among different components and to break down the entire fairly complex network into simple modular components and to use the law of serial and parallel connections to put the probabilities back together in common with the overall success probability of finding a path from A to B.